Множественный перекид. Можно начинать, да?
Good morning. Good morning. Так, Madeline, good morning. I see you here. Так. No, so this week, today it's the last lecture in this semester. So that's why I decided to start with carbohydrates. I know that some groups, first group, will pass this topic, but you still need this information for checkpoint number 4, the last one, the hardest. And as I saw, there are really great number of problems because of drawing some structures and because of understanding of how to explain some of the most important issues of these compounds. If enough time, I will continue with some information about amino acids and proteins you may need this week. Okay, so carbohydrates or sugars. These compounds are known as the more widely distributed in nature. So we can say that carbohydrates are compounds mostly present in nature. What are carbohydrates? For you to understand the most widely distributed, definitely it's a cellulose, which is synthesized due to photosynthesis, as you know, and due to our metabolism, starch and glycogen that are also representative of carbohydrates produce some energy. That's why carbohydrates are compounds can be source of fast energy. Classification of carbohydrates, first of all, depends on how many units of monosaccharide are there. So if there are only one unit, that means not undergo hydrolysis reaction, it's known as monosaccharide. Oligosaccharides, compounds from 2 to 10, sometimes we mention till 20, but mostly from 2 to 10 monosaccharide units. That means due to hydrolysis, these compounds produce such monosaccharides, mostly same, but can be different. And polysaccharides. Polysaccharides means consist a lot. They are polymeric compound, usually very high molecular weight, more than 5,000 definitely, some of them even 1 million and higher. Monosaccharides, let us start first to understand their structure and chemical behavior. So monosaccharides are heterofunctional compounds. They are containing oxo, it can be aldehyde, can be keto group, and few hydroxy group. That's why we can say that monosaccharides are polyols, oxo-polyols, so polyalcohol because of at least 2 hydroxy groups. According to the nature of the oxo group, monosaccharides can be classified as aldoses and ketoses. Suffix -ose typical for monosaccharides and some polysaccharides as well. So aldoses, ketoses, this is according to the nature of functional group, but there can be different long carbon chain. According to how long the carbon chain, according to the number of carbons in the parent structure, they can be classified as trioses, not often but present in nature, tetroses, pentoses, hexoses. If we will combine these both, we will get such classification. So aldoses, that means aldehyde group. It's always first, according to the number in IUPAC system, and number of CH-OH group, they can be different from 1 to 8. So for ketoses, keto group always second position for natural, and from 1 to 7 can be the number of CH-OH groups. For example, these compounds, it's a glucose, it's an aldohexose. We combine 2 classification to classify this compound, naming mainly common. nature important from biochemical point of view, natural point of view, compounds, they all have common names. But necessary to classify some of them. So aldohexose, suffix once, can be keto, tetros, 4 carbons in a chain, keto group there. OH group can be different side. It can be right or left, as you see in glucose, left or right side. Due to this, naming different. So what we know about such compounds? As you saw in the previous, they are present asymmetrical carbon atoms. It's a chiral center. Asymmetrical carbon atom means that they are possible to find stereoisomers. Asymmetrical, that means there are 4 different substituents around. 4 different. That means sp3 hybridized supposed to be. So optical isomers can be and diastereoisomers. Optical isomers, more correct from chemical point of view, we name enantiomers. They can be D and L. Diastereoisomers, they are not look like mirror images. I will show you the picture then. It's a type of stereoisomerism that differs in a spatial arrangement of atoms in the molecule, but not mirror images to each other. Let us see how it looks like. For optical isomerism, for enantiomerism, so let us take glucose as example. So what we see here, 1, 2, 3, 4 asymmetrical carbon atoms here present. Which one we need to compare position of OH group, which one we should check to be sure is a D or L. For aldoses and ketoses, if there we have aldehyde or keto group, oxo group. Last asymmetrical carbon OH group position give us information about is it D or L. Last asymmetrical carbon. If you remember, for carboxylic acids, heterofunctional carboxylic acids, their first asymmetrical carbon OH group position we check. For sugars, as they are aldoses or ketoses, last asymmetrical carbon. That's why right side means D-glucose. Plus or minus depends on nature. So this plus or minus means what angle it's rotate plant polarized light. Is it positive side or negative? This is the nature of optical isomers. They are same in physical, chemical properties, and all physical properties except one. They rotate plant polarized light, different angle, or right or left side, positive or negative side. We can't predict what side it will rotate plant polarized light. It should be measured experimental way. So again, D or L we can see when formula is written. Is it plus or minus? Because it can be D minus ribose, D minus fructose, but D plus glucose, D positive galactose, and so on. Plus or minus, only experimental way can be found, and that's why necessary to memorize. Because of different optical activity, these compounds, they have different biochemistry. We are stereospecific, our body made by stereoisomers. For example, in our body only D sugars, but L amino acids in our proteins. So how enantiomers looks like? They looks like mirror images. All molecule not only last asymmetrical, all molecule mirror image. As you see, it's the same glucose, but L minus because of glucose D positive. That means L negative. Mirror images. Diastereoisomers not look like mirror images. Let us see, as example, let us take mannose. It's different in glucose in the second OH group position. Glucose, for glucose second OH group right side, for mannose it's a left side. And let us compare with the galactose. The compound different from glucose in the fourth one, number 4 OH group position. 1, 2, 3, 4 as you see. So what we see? That they are different OH groups, different in 2 cases, OH group different, but they not looks like mirror images. That's why they rotate plant polarized light, same positive angle, but not the same value angle. This value is different, but positive in both cases. can be situation when there are only here two asymmetrical atoms, OH group position were different. Can be a situation where just one different. For example, mannose and glucose, different only in 1 second OH group position. Such type of diastereoisomers known as epimers. It's one of the diastereoisomers. So how our sugars look like? Monosaccharides, first of all. They can be represented as open and cyclic forms. Why it's so? If you remember, when we discussed aldehydes and alcohols, there was a chemical properties, additional nucleophilic reaction. Aldehydes adds alcohols, hydrogen goes to the minus delta oxygen in oxo group, and OR moves to the carbon, which is positive delta charged. Additional nucleophilic mechanism reaction. In acidic medium, usually it's happen and we have a hemiacetal as result. Compounds with alcohol group and ether group, same moment, bonded to the same carbon. Hemiacetal. So, when we deal with a monosaccharide, there we have aldehyde or keto group, same molecule as hydroxy group. When additional reaction will happen, there will be intermolecular additional with formation of cyclic structure. Same hemiacetal group is formed when hydrogen adds to the oxygen and OR adds to the carbon, but cyclic structure as a result. How it's happened? Let us see using glucose as example. So open fissure structure. Open fissure. Same as I gave you before. These structures are present but only in aqueous medium. They exist, they are present. What percentage I will show you then. What important to know? This structure with one aldehyde group, but 1, 2, 3, 4, 5 hydroxy group. One aldehyde and additional reaction with alcohol. Which one OH group will react with aldehyde additional way? The answer is all of them. Every OH group in this compound can be added to aldehyde group, but not every forming stable cycle as a result of additional reaction. Unstable, they can't exist long. They are trying to be formed and open same moment because of unstable. The most stable cyclic compounds for such saturated situation, 5 or 6 membered. So that's why for glucose and for other monosaccharides essential nature, major product, it's a second last OH group. Not last because of it's a primary, last from secondary. That's why second last from all carbons in this chain. Same procedure, hydrogen adds to the oxygen as oxygen minus delta there, and oxygen adds to the carbon, which is plus delta charged. As result, we can get two possible cases. As here, this first carbon, it's not a symmetrical one, it's sp2 hybridized, that's why this group rotates around sigma bond, absolutely free, not affecting is it glucose, is it D structure or not. So that's why it's possible for this OH group, last asymmetrical, second last carbon OH group, it's possible to form two structures. First one, if aldehyde group was right side, after additional reaction, OH group appears inside the ring. Oh, I'm sorry, here alpha position, it's my mistake. And the second situation, if hydrogen inside OH outside. It's a cyclic forms and they in equilibrium with each other. Through open fissure, they in equilibrium with each other. Open fissure form looks hard and untypical because of really here 6 atoms in a ring, but it's look like there are 4. And the oxygen-carbon bond looks like there we have right angle and it's long, but it's not truth. Oxygen-carbon bond even shorter than carbon-carbon bond. That's why other scientists, Haworth, give other way to draw this formula, much more acceptable, as some chemists think. It doesn't mean that Tollens formula is not correct. It is. It's correct one. Haworth's formula, just a different way to draw it. So that's why it doesn't matter how way it's written in a book. Is a Tollens way written? Haworth means same and the same chemical behavior. So Haworth saw that if they are 5-membered with the oxygen, it looks similar with the compounds heterofunctional compound, heterocyclic compound, we know already. This is pyran. Pyran was aromatic compound, not aromatic, unsaturated compound, with a double bonds, alternate position to oxygen. This one compound in sugar, it's saturated with OH and hydrogen different position, according to the cycle formed after additional reaction. So such structure, 6-membered with the oxygen, which is present inside cyclic structure of monosaccharide, it's a pyranosic structure. Pyran, but O's from sugar. Pyranose. And can be in some compounds 5-membered ring mainly present. This is same as furan. Furan, as you remember, it was aromatic compound. This one now is saturated and it's a part of the sugar. That's why known as furanosic structure. Furan, O's. How this Haworth's formula should be written? So we can construct this formula knowing how Tollens looks like. Let us practice. So to draw Haworth's formula right, first of all, we need to number carbon atoms in this Tollens structure. Starts from the hemiacetal, definitely it was the first because of this OH group formed after additional of second last OH group to the aldehyde. So 6 carbons in a chain. This symbol, 3 lines, it's not a triple bond, this means identity symbol. That means these formulae are same. So let us start. Pyranosic structure, to be written properly, necessary to number atoms in this ring as well. So as you see, oxygen here, it's bonded to the first and fifth carbon atoms in a ring. We start numbering from right to left. Let us check. First one here, and that's why we move clockwise to get first and fifth as result. First and fifth, it's correct. Sixth one will be up or low. Let us see in what case it will be above, what case CH2OH will be below. So now their rule. All groups appears inside the ring in Tollens structure should be written below the ring in Haworth's formula. To memorize easier, just use your imagination. It seems like if we will make this ring be non-transparent, some groups we will not see. Why? Because from our side they will be below. So that's why, let us start, let us see. Second position, OH group inside the ring, that's why it will be below in Haworth's formula. Third one, hydrogen inside, hydrogen should be below. OH group in fourth position, inside, that means it should be below. Problem starts with the first and the fifth one. For fifth one, both outside. That's why CH2OH will be above if it's D structure. For D-glucose, D-galactose, any D structure monosaccharide, CH2OH written above, hydrogen below. If there will be L-glucose, CH2OH will be inside, hydrogen above. So this is necessary to memorize. And the first one, as I told you, there are 2 chances, OH can be inside or hydrogen can be inside. In our case, OH group was inside the ring, it's an alpha position. Name is absolutely same, doesn't matter, is it Tollens or Haworth's formula. Alpha, we indicate asymmetrical carbon, hemiacetal OH group. First hemiacetal OH group. For fructose it will be number 2. But in glucose, galactose, for aldoses, it's always number 1 carbon bonded. Hemiacetal. below alpha, above beta. Then we indicate the parent chain. The parent chain, it's a D plus gluco. D plus gluco. Position of every OH group here because of glucose was the initial structure. And then we need to indicate what is a cycle appears as a result of this additional reaction. Pyranose. You can't name it according to IUPAC system from chemical point of view just alpha glucose. It's not correct. In biochemistry we use this short when we describe some biochemical transformation, knowing that mainly it's a glucose 6-membered ring present in nature. But it doesn't mean that 5-membered not found there. They are found in aqueous medium. And from chemical point of view, you know, when we name any compound, one name, one formula is supposed to be corresponded to. If they're possible to draw two different cyclic compounds for glucose, 5 and 6-membered, we can't ignore this name in an IUPAC procedure. Cyclic structure, we need to indicate what cycles there. That's why alpha D plus glucopyranose, not just glucose. Glucose in chemistry in IUPAC we use only for open fissure. O suffix once to gluco. So now as example let us practice as a submodule. It's a checkpoint number 4 question necessary to write formation of cyclic form. For one of the monosaccharide you should memorize. It can be ribose, glucose, galactose, mannose or fructose. So let us practice. I took fructose as example. So formation of cyclic form, that means it's a chemical reaction. So fructose, it's a ketohexose, second position keto group. All other groups here, third, fourth, fifth, they are same as in glucose. It's a D because of last asymmetrical OH group right position, and minus because of nature of this substance. It's experimentally way measured angle. So we know that in equilibrium, this open fissure with the cyclic structures, it's in equilibrium with. That means this equilibrium can be shifted, it's dynamic one. Second last OH group adds to the keto group. Here can be two cases. OH group can appear inside the ring, or CH2OH can appear inside the ring. As Tollens formula, here we use as intermediate because of mainly, and it's easier to deal with the Haworth formula. That's why I left both above, both outside, finally to show two Haworth formulae from one Tollens structure. So D minus, fructe, it's a name of this structure, and suffix furanose as it 5-membered oxygen and 4 carbons, it's a 5-membered ring. It's not alpha, not beta, because of none of the groups inside. It seems like it's a mixture of two anomeric structure. This group, OH group, bond as a result of additional reaction of aldehyde or oxo group with a hydroxy group. It's a hemiacetal OH group known as anomeric hydroxyl, and that's why this alpha beta known as anomers. So identity symbol between Tollens and Haworth formula. It's not correct to use here one arrow from chemical point of view, because of when we write arrow means transformation, that means process. But here we not produce, it's not produced Haworth formula from Tollens. Their identity, we can draw one of them. No, or in our case, we use Tollens structure as kind of helpful information, as an intermediate, not real, but just theoretical intermediate, to write Haworth formula properly. So let us draw the Haworth formula. Tollens must be numbered. We see that oxygen in Tollens structure of fructose, it's bonded to the second, not first, second and fifth. That's why we start numbering in ring from second. 2, 3, 4, 5, let us check. Oxygen bonded to the second and fifth. It's truth. Now let us arrange our groups or above or below the ring in Haworth formula. So all groups inside the ring should be below. So third one, hydrogen below, OH above. And fourth one, OH below, hydrogen above. For fifth one, I want to remind you that if it's D-fructose, CH2OH above, hydrogen below. And there are two possible cases. Or OH appears inside to be below, that means it's an alpha position, CH2OH above. Alpha D minus fructofuranose. And same chance, not 50-50%, usually one of them a little higher due to what it was, glucose, fructose, ribose, but approximately very high percent. No, not same, but very high. Both present. Definitely both of them present. We can't ignore one of them. In a mixture, that's why plus between. In a mixture present second type of Haworth formula, second cyclic structure, where OH above, anomeric OH above. It's a beta position. Beta D minus fructofuranose. They are both fructofuranose, both D minus. But one of them alpha, one of them beta. When we deal with the sugars physical state, we know that they are solid crystalline, solid substances. Soluble in water, when we're talking about monosaccharides, quite good soluble. So when they are solid, they are 100% cyclic. Doesn't matter, is it glucose, fructose, they are cyclic themselves. But when we dissolve the substance in aqueous medium, in water, some number of cycles open to form in equilibrium some percentage of open fissure structure. This percentage usually very, very small. Because of inequilibrium between open fissure and cyclic forms, when we dissolve some, for example, just alpha D plus glucopyranose in water, because of their inequilibrium with open fissure, and after some time, some short time, sometimes longer, the equilibrium appears between alpha and beta forms, and they both starts to be present. This change of optical angle, because of both alpha and beta, the same positive angle, both positive angle, but alpha and beta glucose, they have different positive. Glucose alpha, higher positive, it's 112, and glucose beta nature, just plus 19. For different monosaccharide, percentage of alpha beta different, so that's why it will affect the average finally appears. It's not just exact average, it depends on percentage of alpha and beta form finally in aqueous medium. So after we dissolve alpha glucopyranose in water, optical angle was the highest, can be 112. But because of equilibrium dynamic one, after time it becomes lower till the equilibrium state 52.5. Then it will be not changed if we will not apply some stressful factor. Equilibrium. So it's change of optical angle of newly prepared solution of monosaccharide with time due to the equilibrium known as mutarotation. So how it look like for glucose? When we deal with just one of the cyclic structure, for example alpha, in aqueous medium when equilibrium appears, there's 36% of alpha approximately and 64% of beta. Beta more symmetrical, that's why. 64 and 36. Together it should give us 100 because of very small amount of open fissure present, but present. It's much less than 1%. And 5-membered ring also present, less than 0.1 but higher than open fissure. So that's why it's so essential to name cyclic structure properly. In an aqueous medium we can find glucofuranose, but we can't even compare the value of this glucofuranose with the amount of glucopyranose, much more stable case. But equilibrium between them, and that's why we can shift. If we will add to this aqueous solution some substance chemically can react with aldehyde group, with the open fissure structure. Equilibrium shift to the open fissure, and as a result we have chemical reaction, sometimes even complete one. If there we will add some substance chemically can react with a cyclic form, like alcohol for example, there we will get equilibrium shifts completely to one of the cyclic structures. What kind of chemical properties are there? I will mention some, the most important for you to know this semester. So again, can be chemical properties appears because of the open fissure structure aldehyde group present. So one of them is reduction, second one oxidation. These are the most important. So what about reduction? Aldehyde group can be reduced much easier than oxo group. So here we dealing with, for monosaccharide as well as for other sugars, we're trying to avoid two stressful factors because of they can destroy carbon-carbon bond and leads to formation of mixture of products as a result, sometimes even unpredictable mixture. So what about reduction? We use mild reducing agent like lithium tetrahydroaluminate, and this mild reducing agent reduce only aldehyde group to form polyalcohol. I took galactose, it's a D plus galactose, it's forming dulcitol. Glucose forming sorbitol. These polyalcohols, they are not sugars anymore, but they are with a still sweet taste, not as sweet as, for example, sucrose or glucose, less, but it's still sweet taste. And that's why for people who suffering because of problems with the glucose metabolism, like diabetes mellitus, for example, they can use this dulcitol or sorbitol as something can be used in a diet instead of sugar. These are polyalcohols. Oxidation. There are 3 types of oxidation, even 4 types of oxidation can be there. The first one is a mild reducing agent in neutral or acidic medium. The easiest case when we use bromine water is oxidizing agent. Do not show what will happen with bromine water due to this reaction. We use oxidizing agent, we indicate it above the arrow, and show just product of initial substance. This is mannose, D positive mannose, oxidation product. So only aldehyde group can be oxidized in this mild condition. Because of aldehyde group, you know, some percentage even can be oxidized by oxygen in air. Small percentage, but can. That means not alcohol group, just aldehyde group can be oxidized. And it's a mono carboxylic acid, but polyalcohol. It's a heterofunctional carboxylic acid, hydroxy acid, and they have a common suffix, onic acid, to show that this is such nature polyalcohol. So mannose was become mannonic, mannonic acid, gluconic, galactonic, ribonic. If there we will use something stronger as oxidizing agent, for example nitric acid can oxidize not only aldehyde group, but primary alcohol group as well. As a result, they are dicarboxylic acid with a unique position OH group there. It's a suffix aric acid, ARIC, aric acid, glucaric, galactaric, mannaric. This was glucose, that's why glucaric acid. Can be oxidation in cyclic form, where 6,1 OH group oxidize primary alcohol, but aldehyde group staying same as it was. Open fissure form, such oxidation can't happen because of doesn't matter what oxidizing agent we use, aldehyde group will be oxidized. If we will take just aqueous medium of any sugar as an equilibrium open fissure structure present, we can use any oxidizing agent, there will be chemical reaction with aldehyde both. So that's why if we need to oxidize just 6,1-OH group and not the aldehyde group, we need to protect somehow our aldehyde group from oxidation. That means we need to not allow this OH group to form open fissure form back. How it can happen? By protection with the alcohols. So the first step, if you need to describe formation of uronic acids, so I took glucose as initial, that's why we will produce glucuronic acid, urine, it's a familiar word supposed to be. So we will produce alpha glucuronic acid. So I took alpha D plus glucopyranose, and I need to protect this OH group, first OH group, from oxidation. Reaction with alcohol. It can be methanol in a flask or ethanol in a flask, acidic medium. It's the same as formation of ether we discussed in a topic alcohol, as you remember. Acidic medium, what's happened? Alcohol group of alcohol react with hemiacetal group, the most reactive group in our sugar, as it formed due to additional of second last OH group position and aldehyde group. That's why it's in equilibrium between oxygen and carbon here. So it's in equilibrium, that's why the mobile one. So these two OH group reacts with each other, losing water. It's substitutional nucleophilic reaction. So as a result we have ether, but it's not same ether as we discussed. It's a ether group but with a sugar, with a monosaccharide. Such compounds are quite active and known as glycosides. That's why we need to name this compound according to IUPAC. What way? We name what substituent here. It's a methyl, one methyl, or one methyl like some students name, one methyl. Then what we need? We need the parent structure, it's our sugar. It's a alpha D plus glucopyran, and now we change suffix us into ozide, pyranoside, glycoside, pyranoside, suffix ozide. So now group is protected, and if you need just a chemical property to describe a reaction of monosaccharide with alcohol, this is it. This is a chemical reaction, appears in nature, everything fine. But if you need then to produce glucuronic acid, we can oxidize now, and we can use oxidizing agent. It can be strong one like nitric acid in a flask, but in our body formation of glucuronic acids happen as well, and there can't be in nitric acid use. There we use mild oxidizing agent because of this is enzyme oxidation. So due to this reaction oxidation, only primary 6 position OH group will be oxidized, and they are monocarboxylic acid but not glucuronic yet because of methyl group still there. To be glucuronic acid, they are supposed to be free OH group to be in equilibrium with open fissure structure. That means hydrolysis is supposed to happen. Due to hydrolysis, acidic medium, acidic hydrolysis, this OCH3 group destroyed to form alcohol back. It was used to protect just, and our hemiacetal group, the anomeric OH group, is released free. This is alpha D plus glucuronic acid. This acid in equilibrium with open fissure structure. That's why it's possible to get open fissure with the first position aldehyde group and last carbon carboxylic. Now let's talk about, can be one more, oxidation. It's a test reaction for aldehyde group. You should know. It's an oxidation in alkaline medium. Silva mirror test or Tromer test. It's the same oxidation but in alkaline medium, and aldehydes, doesn't matter is it glucose, galactose, mannose, ribose, they all give us set of reaction, test reaction typical for aldehydes. So disaccharides, the easiest case of oligosaccharides. Sometimes we even separate them in classification. Disaccharides and then oligo more than 2. But chemists prefer to deal with oligos starts from 2. So, the formula C12 or H22 or 11, mostly for all of them, we're interested in. So, from all huge number of disaccharides present in nature, you need to know just 2 types. Among reducing sugars, you need to memorize maltose, lactose, and cellulose structures. We will see how they look like. So what's mean reducing sugar? Here just, it's not maltose, lactose, or cellulose, it's just example of reducing sugar. Disaccharide formed as a result of 2 monosaccharides combined with each other with a unique nature bond, glycosidic bond, because of glycosides we discussed just a few minutes ago. So glycosidic bond can be different. It can be alpha or beta, can be O or N, and glycosidic bond then you will see in nucleic acids. And it can combine different kind of carbons, 1, 2, 1, 4, 1, 6 glycosidic bonds. All of this glycosidic. But in all cases, they are first monosaccharide bonded to the second with glycosidic bond. Second one, monosaccharide, can be bonded using hemiacetal group with the previous monosaccharide. I can be bonded with any other OH group except this. So when this OH group, hemiacetal group, is free, that means this compound in equilibrium with open fissure structure. And that's why can give a set of reaction typical for monosaccharides. It can give silver mirror test even. Such substance, such compounds known as reducing sugars. Non-reducing sugars from non-reducing, you should memorize only sucrose. This is not sucrose formula, it's an idea of non-reducing sugars to be 2 monosaccharides bonded to each other because of reaction of their hemiacetal groups. That's why this bond not alpha, not beta anymore. It's just O-glycosidic bond, and such compounds can't give us silver mirror or Tromer test. That's why known as non-reducing. So how this equilibria look like? For reducing sugars, I took maltose. It's a product of partial hydrolysis of starch. So why this maltose is reducing sugar? For you to know, maltose can be alpha, can be beta. To be alpha maltose, only this one I indicated with the color, asymmetrical. So hemiacetal anomeric OH group position important to be alpha or beta for maltose. All other groups, the nature of the bond can't be changed. It's a maltose in all cases. Just OH can be above, can be below. To be alpha maltose or beta maltose. As a product of partial hydrolysis of starch, we will get alpha maltose mainly because of the alpha glucose structural unit of starch. But because of equilibria between open fissure and cyclic form for all reducing sugars, after we dissolve, we will get product of partial hydrolysis of starch, alpha maltose. After some time, after maybe few hours, we will find beta maltose in a mixture. So take a look what's happened here. The bond here, it's a alpha because of anomeric OH group, hemiacetal OH group of the first monosaccharide. It was alpha position. Alpha, oxygen, because of oxygen bond them to each other. And here bonded first carbon with the fourth carbon. That's why it's an alpha oxygen 1,4 glycosidic bond. So here everything fixed, and this bond can't be opened due to equilibria between open fissure and cyclic form. But this anomeric OH group is in equilibrium. Hydrogen moves to the oxygen, second last one, and double bond here appears. Aldehyde, hemiacetal. Aldehyde, hemiacetal in equilibrium with each other. No, definitely in aqueous medium, equilibria shifts to the cyclic form, but as I told you, a very small percent of open present, and if we will add here a complex of silver, we will get silver mirror test. For non-reducing, for example, sucrose. Sucrose can't be alpha or beta because of their both alpha position glucose bonded to the beta position fructose with an oxygen 1,2 glycosidic bond. It's an alpha and beta same moment. That's why we say it's just O glycosidic. First with the second, oxygen 1,2 glycosidic bond. How to name these compounds? For all biochemically important, we're dealing with the common names. They have maltose, cellabiose, sucrose, and some other. That's why you need to memorize these names. We can't help. In biochemistry, we never dealing with the IUPAC naming of disaccharides. But we need to practice, as they are not only biochemically important substances present in nature. So take a look. Naming of cellabiose. So cellabiose, it's a product of partial hydrolysis of cellulose. They are beta glucose only. So here disaccharide, beta glucose can be bonded with glucose alpha or beta nature. If they are alpha OH group position, there will be alpha cellabiose. OH above will be beta cellabiose. As a product of partial hydrolysis of cellulose, we get in beta cellabiose. Again, after some period of time, we will get alpha in a mixture. But they are both are cellabiose. Difference only in first OH group position. So how to name this compound if we need to name, and how to indicate the nature of the bond? So OH group formed as a result of additional reaction of aldehyde group with a second last OH, the most active. That's why suffix depends on this group. With this group nothing happened to. That's why the second monosaccharide unit will have same suffix it was. That's why we accept it as a parent chain. And the first monosaccharide unit becomes a prefix as a substituent. So the bond here, it's a beta because of first monosaccharide was above, and oxygen because of oxygen combine these two monosaccharide units first with the fourth. That's why 1,4 glycosidic bond. It's important to know because of we need in a naming to indicate how these monosaccharides bonded to. Same as lactans. Okay, let us start. First monosaccharide unit we use as a prefix, and it has same name it was for monosaccharide with a change in its suffix. If you remember, when alcohol, any methanol, ethanol, losing OH group, it gets suffix YL. No, it was methanol become methyl. It was ethanol become ethyl when OH group is lost. Here same case. It was glucopyranose become pyranosyl. But it's still beta, it's still D positive, it's still glucopyranose. Glucopyranosyl. Now we need to show where this bond, where this monosaccharide unit in. We indicate the part of the glycosidic bond name. That this first monosaccharide, with the help of oxygen, through oxygen, first fourth position bonded to the second unit. Second unit, same name as it was for monosaccharide. It was alpha. That's why it's alpha, D plus, and still glucopyranose. See such long, but if no one asks you to name according to IUPAC, you shouldn't. But when you see the formula, you should know how to draw the structure and should know how to recognize what this disaccharide, what is the common name of this disaccharide, if the IUPAC name is written. Again, cellabiose, it's a product of partial hydrolysis of starch. No, not only, but it's formed due to, and it can be alpha or beta because of its reducing sugar. Maltose can be alpha or beta because of its reducing sugar. And we have one more unique sugar, it's lactose. They are galactose combined with glucose. Same beta oxygen, 1,4-glycosidic bond. Sucrose is non-reducing, but doesn't matter what disaccharide. Doesn't matter. All of them chemically can react with water to undergo hydrolysis. Acidic hydrolysis, alkaline hydrolysis for sugar, not typical. For lipids, they are. For monosaccharides, for sugars, only acidic hydrolysis. So what's here happen? If you need to write, if you need to explain chemical behavior of disaccharides. No, so first of all, if they are reducing sugar, they gives all typical reaction for monosaccharides, for open Fischer structure. As when it's non-reducing, they are aldehyde group reaction absent. So hydrolysis of sucrose. What water do? It destroyed glycosidic bond. As a result of this, there are two monosaccharides are produced. There was alpha position glucopyranose, and it's still formed alpha D plus glucopyranose. Please again, don't name it glucose. It's not correct from chemical point of view, as glucose can be 5 or 6 membered in cyclic form. That's why chemical name of substance alpha D plus glucopyranose, as only one structural formula should be possible to write if their name is mentioned. If there will be alpha D plus glucose written, that means we can draw two formulae, pyranosic and furanosic, as I gave you before in equilibria. They are present in aqueous medium both. Definitely very small percent of furanosic form, but it is. So, and second compound here, was a beta fructofuranose. So beta D minus, minus plus, so again I will remind you that they appears because of nature of compound, it's a really measured angle, fructofuranose. So that's why it's interesting to understand that fresh prepared sucrose and sucrose after some time, they behave different way according to optical activity. Fresh prepared sucrose, I don't remember, gave you, no. Fresh prepared sucrose give us positive angle rotation. But because of hydrolysis, with time, positive and negative rotation appears extra, and minus for fructose bigger than plus for glucose. As a result, it was positive angle. After hydrolysis appears, it can be complete. With time, it changed positive into negative. This is inversion. Please be attentive, not mutarotation. Mutarotation is change of optical angle because of equilibrium between of alpha and beta structures. And it's not change, there are no change in a sign. They are change in a value. It's still positive, but bigger or smaller positive than it was. For inversion, their change of sign from positive to negative or from negative to positive, change of sign. So polysaccharides now. Polysaccharides, according to the nature of monosaccharide unit there, can be classified as homopolysaccharides. That means complete hydrolysis of such compounds gives only one nature monosaccharide. That means they are monosaccharide, only one nature. Heteropolysaccharide, they consist more than one type of monosaccharide. That's why complete hydrolysis produces mixture of different monosaccharides. So among huge number of homopolysaccharides, you should know structure of starch, cellulose, glycogen, just to know how it looks like because of its starch analog for humans, chitin, no, dextrins, just according to classification. Heteropolysaccharides, what formula you need to know? Just two. It's a gyaluronic or hyaluronic acid and chondroitin 4-sulfate from all chondroitins. So let us see how these compounds look like. Starch, it's a mixture of two units. It's amylose and amylopectin. Amylose, it's a not so high percent as amylopectin, it's a 10, maximum 20%. But it's present there, and that's why starch gives us set of unique reaction typical as, for example, reaction with iodine. It's a test reaction for starch, as you remember. So the formation of blue, intensive dark blue colored solution when iodine we add to starch. Why? Because of a unique structure of amylose. It's a starch again, some important component. What is how amylose look like? Starch, it's a homopolysaccharide because of it made by only one type of monosaccharide, alpha D plus glucopyranose. Alpha glucose there only. And it's bonded with a unique nature bond, alpha oxygen 1,4-glycosidic. That's why it's clear that why partial hydrolysis of starch produces maltose as a structure. Maltose, there was OH and here OH also, disaccharide with alpha oxygen 1,4-glycosidic bond between monosaccharide units. For amylose, is it polymeric? We have N times glucose fragment. So how the bond is alpha oxygen 1,4-glycosidic bond. So how it look like? Because of the conformation of this glucose cyclic structures, you know, it's bath or chair, right? Chair, the most common. So what is here happened? Because of this polymeric structure, seems like it's in one line, but conformation not allow them to be in one line, one chain, straight one chain, be bonded. It's form a spiral form, spiral structure. And that's why the chemical reaction with iodine happened, because of iodine forming complex. Iodine forming complex, it's fixed inside this spiral structure, and this complex is intensive blue. For amylopectin, which is not spiral but branched structure, so there this reaction impossible to find. And because of human glycogen looks like amylopectin, not as amylose, but amylopectin, our human glycogen not give such reaction with iodine as a starch do. So amylopectin branched because of except alpha oxygen 1,4-glycosidic bond, same as in amylose. It has one more, alpha oxygen 1,6-glycosidic bond. Not every it says not every monosaccharide units in a chain structure forming these branches, and depends on nature of the polysaccharide. But as a result, we see such amylopectin shape. Human glycogen looks just more branched. Cellulose. Cellulose, it's a homopolysaccharide because of the unit of this structure is a beta glucose only. That's why complete hydrolysis of cellulose gives us only one product, it's a beta D plus glucopyranose. So the bond between monosaccharide units, because of there was a beta glucose, beta oxygen 1,4-glycosidic bond. This is the difference between starch and cellulose. The different nature bond. That's why starch can be source of energy for us. We have enzyme for hydrolysis of starch, but no enzyme for cellulose hydrolysis. Partial hydrolysis of cellulose give us cellobiose as a structure. And heteropolysaccharides. You need to know just two of them. Hyaluronic or gyaluronic acid. As you see, if in previous cases there was diosic fragment and not monosaccharide, as there was just alpha D plus glucopyranose unit n times, or beta D plus glucopyranose unit n times. Here we have not diosic fragment where two monosaccharide units combine with each other. Take a look. What structural units we have in hyaluronic acid? First unit, it's a glucuronic acid, beta D plus glucuronic acid, COH6 position, and it's bonded beta oxygen 1,3 glycosidic bond with a second unit, which is supposed to be glucose, but it's not glucose. There it's a N-acetyl glucosamine, N-acetyl glucosamine, beta structure of N-acetyl glucosamine. So we don't have here glucuronic acid and N-acetyl glucosamine because of their bonded. That's why this substance is produced after complete hydrolysis of hyaluronic acid. Two types of bond. First type inside the monomer between these two units. It's a beta oxygen 1,3. Between monosaccharide units, between monomeric units, they are beta oxygen 1,4 glycosidic bond. Because of this fragment N-acetyl glucosamine, beta oxygen 1,4, 1 with a fourth bond forming polymeric structure. And one more heteropolysaccharide, it's a chondroitin 4 sulfate. It looks similar with hyaluronic acid, with one difference. Not glucose fragment, but galactose fragment. And it's not just galactose, but galactose sulfate. It's an ester with sulfuric acid. So that's why this is chondroitin 4 sulfate, fourth position sulfate here. But it's still N-acetyl. So that's why complete hydrolysis of this chondroitin 4 sulfate forming beta oxygen glucuronic D plus glucuronic acid and beta D plus N-acetyl galactosamine sulfate. Bond nature still same, beta oxygen 1,3 glycosidic bond and beta oxygen 1,4 glycosidic bond. So with sugars, I hope everything clear. Так. I hope it's visible. And let us continue with the amino acids. There are few words. 10 minutes left. I want to give you some classification. Так, how to... Amino acids. So, amino acids are heterofunctional compounds. Can be defined as heterofunctional compounds containing both amino group and carboxylic group in same structure. Due to how they are bonded, to what position amino group bonded to the carboxylic, according to carboxylic, amino acids can be classified in our as alpha, beta, gamma amino acids. Only alpha amino acids are structural units of our proteins. We are made by alpha amino acids as a proteins, right? So alpha position, it's a second position according to the carboxylic. As a cis alpha position, carbon is asymmetrical for all except one amino acid. I will show you then the structural formula. So any radical except hydrogen, it will be asymmetrical carbon atom. That's why amino acids can be also two types according to the nature of isomerism, stereoisomerism, optical isomerism for amino acids as well typical, and it's essential to know because of, again, we are stereospecific. In our body present only L alpha amino acids. L alpha. This is alanine is the easiest one. One of the easiest, one of the most common amino acids. L amino acids are known as natural. It doesn't mean that D amino acids, now we're talking about amino group position according to the carboxylic. take a look. To write this isomerism properly, we should write the chain, carbon chain, same as it was in aldehydes for monosaccharides. There was aldehyde group above, here carboxylic group above. The chain from first to the last we can number, and amino group first asymmetrical, see, amino group position we check to decide is it D or L alanine in this case. D amino acids also can be found in nature, not in our protein. They are not natural for us. That's why natural L amino acid, D amino acids, not natural for us, but they can be found in bacterial, for example. So, natural. Second classification of amino acids, it's a classification according to the nature of radicals. Radicals can be, same as for any functional group compounds, classified as aliphatic and cyclic. Aliphatic, here branched or not, inside this group there can be extra functional groups present. So aliphatic, as example valine, shorter vowel, aromatic and cyclic. Here we separate them because of they have different behavior, let us say so. They are both cyclic, but aromatic here can be homo, heterocyclic, but they give us plate, and that's why unique structure when they are classified, when they are stabilized as secondary, the tertiary structure of proteins and quaternary as well. So aromatic, for example, tyrosine, or phenylalanine if there are no OH group. Heterocyclic, only one not aromatic heterocyclic you need to know, it's a proline. Unique structure because of amino group, here present in a ring. It's secondary. Second classification, third one already, it's a classification according to the polarity of the radical. They can be polar or non-polar. Biochemically, this polarity we indicate with the words hydrophobic or hydrophilic according to the behavior, and then according to the nature of the bond in polymeric structure in proteins. Hydrophobic, that means not polar. And hydrophilic, all amino acids are polar structures. They are polar, cyclic, solid compounds, soluble in water, they are polar themselves. But when our amino acids combine in a polypeptide chain, polar group, carboxylic and amino groups are bonded, and that's why polarity finally of polypeptide depends on nature of radical. Radical can be non-polar, like benzene ring, like CH3 group, alkyl radical, and can be with some functional groups extra present to become hydrophilic. Due to what extra groups present there, hydrophilic can be classified as hydrophilic uncharged if there is something polar but not able to dissociate. For example, alcohol group. It's a polar group but not electrolyte group. It's not dissociate ever. So what here we see, that radical will be polar but not charged. This is serine. You saw this compound already in lipids topic. So can be positively charged if they are side chain basic group. Why it's a basic group become positively? Because of we classified according to biochemically important pH 7.4. It's alkaline medium. That's why for basic group it will be protonized in such way. They are protonized in our body. So that's why here will be NH3 plus. 7.4, it's almost neutral. That means it's acidic for strong basic for amines. So positively charged, that means extra amino group, extra basic group present in our radical. And can be negatively charged with a side chain acidic group extra. Here, for example, glutamic acid. It's extra carboxylic group. CO minus then finally will be. And one more classification, it's according to the physiological role. All amino acids can be classified as essential, can be and non-essential. Non-essential can be synthesized in our body, but essential cannot. Essential alpha amino acids which can't be produced in our body at all, or can't be produced in sufficient amounts by the body, and therefore must be obtained from the diet in order for normal protein synthesis to occur. So essential amino acids must be present in the body. So there are not so many essential. For adults, as you see, there are 8 only. For kids, there are 10, 2 more. 2 more basic than you will see. So for adults, valine, leucine, isoleucine, they are alkyl groups. Methionine, sulfur containing. Phenylalanine, it's aromatic, benzene ring there. Tryptophan, it's a heterocyclic aromatic, nitrogen containing. Threonine, oxygen containing. And lysine, basic NH2 group containing. They're all essential, and from them then other amino acids can be synthesized by our body due to some different processes. So when we deal with amino acids, anyone, themselves are solid crystalline. So when we draw this formula, it's necessary to understand it's a formal, imaginary, unreal structure. Why? Amino group is basic and carboxylic acidic, and they are bonded to the same carbon. Can't be situation, they will not affect each other. It's same as we mix acid and base in same flask. There will be neutralization reaction. That's why this never happened. What happened really? Even in cyclic structure, when we deal with a solid, when we deal with a solid, there we're dealing with a Zwitter ionic 100%. What's mean? Zwitter, it's a German, means 2, male and female in one. Hydrogen from carboxylic moves to the amino group to make it NH3 positive and leaving behind CO minus. It's still neutral, but now it's a Zwitter ionic structure, neutral. Due to what pH medium this solid crystalline amino acid dissolved in, they are possible to get different charge of amino acid. So remember proton loss, proton gain, as we have the NH3 plus and CO minus. So what is isoelectric point for amino acid or protein? A symbol Pi, it's a pH value at which the concentration of Zwitter ionic structure is a maximum, and the minimum concentration of cationic and ionic structures are equal to each other, and that's why neutralize each other. Never happened that just 100% Zwitter ionic in aqueous medium. Why? Because of the equilibria between Zwitter ionic structure and cationic and ionic forms. And if equilibria, that means there will be both present, and they are just necessary to understand if they are isoelectric point, cationic and ionic, very, very small amount, and they neutralize each other. So let us try to understand how this equilibria looks like. So this already chemical behavior of our amino acid. We know this as acid-base properties. So Zwitter ionic, solid, we dissolve in water, and if pH of this solution will be equal to Pi, the charge of this amino acid equal to 0, and if we will use something like electrophoresis, it will move nowhere in electric field. So if there will be, if then we will add some little amount of acid, if acidic medium is produced, what happened then with Zwitter ionic structure? Hydrogen from the medium goes to the negatively charged part of the amino acid, plus attract to the minus, forming COH, but with a protonized amino group nothing happened already. It's already protonized. That's why finally this amino acid in acidic medium, it becomes positively charged. In our case it's +1 charged because of a radical I took some hydrophobic or not charged. So it's a cationic structure, and if you see there are equilibria between, and this equilibria illustrate dissociation of carboxylic group. That's why from physical point of view it can be described with pKa carboxylic group. What will happen in basic medium? In basic medium, proton lost from isoelectric point zwitterionic, proton can be lost only from NH3 positive. Carboxylic group already lost. And that's why there we have anionic structure where minus because of carboxylic group, and net charge is -1 for hydrophobic and hydrophilic not charged. This behavior, this equilibrium illustrate with dissociation of NH3 plus group. It can be pKa or pKb for NH2, the same value. So how to determine the isoelectric point for amino acid? As it in equilibrium with two cationic illustrate as pKa1 and pKa2, the average of these two values, it's an isoelectric point value. If there will be not amino acid but protein or even polypeptide or even tripeptide, we can't calculate isoelectric point. Only for amino acid it's possible to do. In other cases, isoelectric point can be found only experimental way. Only experimental way. We measure where, what pH our protein doesn't move in electric field. And this is isoelectric point as it will be zero charged. So there are chemical properties of amino acid. They are all properties typical for amino group and carboxylic as they are heterofunctional. So there are few chemical properties you must know. I will have time to show you some of them, and they can be divided into basic properties and acidic properties. Among all huge number of amino group reactions, you should know few. It's a formation of salts because of mainly we use amino acid, we use them in medicine, and they are present in as a solid state also, as they are crystallized out from exact pH. They are present as a salts. No, it's sometimes it's a way even to increase absorption. So what salt formation can happen? If we will add HCl or any other acid, basic group will react with, forming hydrochloric salt or hydrosulfuric salt, any salt, due to what acid? Suffix not changed because of carboxylic group, nothing happened to. If we will add sodium or potassium hydroxide, their carboxylic group will react with. But now we mention formation of the salt because of addition of acid. Second, essential for you to know reaction, it's a reaction biochemical important, deamination. It's not a human body. We have no such enzyme, aspartase. But it's a biochemically important reaction, formation of unsaturated carboxylic acids. So L-aspartic acid, due to with the help of aspartase, deamination happened, amino group from one carbon and hydrogen from second one, forming unsaturated fumaric acid. In our body happen oxidative deamination with the help of enzyme, no oxidase enzyme. In this case, there can be different names, but this is oxidase 4. It's a common. So what's happened due to oxidative deamination with, for example, phenylalanine? First step, enzyme take two hydrogen atoms from this structure, where from amino group 1 and from alpha carbon second one, forming alpha amino acid. And then these compounds are unstable and react with the water quite readily. Addition of water leads to elimination of ammonia, and as a result their keto acids are formed. Phenyl pyruvic acid. And one more reaction I want to show you. We have no time, but you need this to write in submodule number 4. transamination reaction from chemical point of view, how to write it properly. Take a look. Transamination is a synthesis of amino acids from other with the help of keto. It's a biochemical process, so that's why without enzyme it never happened. Enzyme, coenzyme, everything happened with the help of these compounds only. In this case, transaminase, I took aspartic acid, and second biochemically important ketose we need. Keto, in our case, alpha ketoglutaric acid. You was told to memorize these compounds. Here, instead of alpha ketoglutaric, can be oxaloacetic, acetoacetic acids, pyruvic acid can be. So different nature keto acids. So what's happened due to these transaminations? Just exchange alpha amino acid group from amino acid, exchange with the keto alpha keto group of biochemically important keto acids. As a result, we have new keto acid and new amino acid. Not necessary to name them. This is oxaloacetic, this one L-glutamic acid. No, this is it for today. Carboxylic group reactions, biochemically important, I will show you just fast way. It's also formation of salts, formation of ester for separation of amino acids, and decarboxylation reaction. It can be with a heating. In our body, it's an enzyme reaction. It's a formation of biogenic amines, losing of carboxylic acid, carboxylic group in a way of CO2. So lecture is over. I saw again a huge number of students late, so I was very disappointed. It's the last lecture, and it's disrespect to lecturer. I want to remind you this. So lecture is over. Goodbye. My group, see you today 2:40 as you remember p.m. Goodbye.